This diagram breaks down the two ways we can extract energy from the nucleus of an atom. On the left is fission, splitting heavy atoms like uranium to create power, a process that leaves behind radioactive waste. On the right is fusion, which forces two light atoms together to form a larger one, producing massive amounts of energy with almost no dangerous byproducts. Fusion relies on abundant materials like deuterium, an isotope of hydrogen. If you look closely at this image of the sun, the violent solar flares are visible evidence of this process happening at a massive scale. Replicating this stellar engine on Earth has historically required massive, state-funded facilities. The engineering challenge is so high that only national governments could afford to attempt it. Take a look at this photograph of China's East Superconducting Tokamak. These reactors, along with multinational projects in Europe, require billions of dollars in national investment and decades of engineering just to become operational. India's domestic fusion research has traditionally followed this path. Highly guarded programs run exclusively by the government's Department of Atomic Energy. For decades, the logic was simple. Capturing the energy of a star required superpower-level budgets to build increasingly gigantic machines. But an emerging team in India is challenging that logic. Beneath this Bengaluru skyline, a 2-year-old startup named Pranos Fusion has taken a different path. Using roughly $417,000 in seed money, this team successfully built India's first privately developed fusion reactor. They call it Pragya. This scale comparison graphic shows exactly how radical their design is. On the left, the International ITER reactor stands with a massive 6.2-meter radius. On the right, Pragya measures just 0.40 meters. Why would a private startup intentionally build a machine the size of a kitchen table to compete in a global race defined by machines the size of apartment buildings? The answer lies in the hardware. This diagram shows a simplified tokamak, a specialized donut-shaped vacuum chamber for nuclear fusion. The process begins by injecting gas and heating it to millions of degrees, forming superheated plasma. Because this plasma is hotter than the sun, it would melt the physical walls on contact. To prevent this, powerful magnetic fields force the glowing plasma into a tight ring, keeping it suspended in midair. The engineering hurdle is that plasma is highly unstable. It violently thrashes and fluctuates, and any small flicker in magnetic containment instantly kills the reaction. Achieving fusion requires solving a massive, complex control problem, maintaining stability at temperatures exceeding 100 million degrees. Pranos Fusion designed Pragya specifically as a hardware testbed, a platform for refining the specific technologies needed for future power plants. The reactor operates with a 0.1 Tesla magnetic field and a plasma current between 20 and 25 kiloamps. These specific parameters provide the environment needed to test the startup's real product, a custom plasma control software named Giga. This software is designed to predict those erratic plasma fluctuations and adjust the magnetic fields in real time to contain them. By keeping Pragya small and low power, the engineering team can run thousands of software iterations rapidly. They can fail, tweak the code, and try again, without the financial risk associated with testing on a billion-dollar facility. Before a grid-connected fusion power plant can exist, researchers must perfect the software required to control the reaction. Pragya is a low-budget simulator built to write that exact code. The emergence of private fusion reflects a shift in how India manages strategic technology, mirroring the recent privatization of the space sector. Commercial spaceflight moved from slow-moving government rockets to rapid, iterative private launches. Now, the fusion sector is entering a similarly agile commercial phase. Pragya's development clears a path for a new ecosystem of private Indian startups, with companies like Hland and Anubal Fusion now entering the field. For the first time, India's fusion development is no longer confined solely to state labs. Projects like Pragya signal a transition for India, moving from software-centric development into the complex physical engineering required for deep-tech power systems. You can see the academic weight behind this shift by looking at this historic campus, the Indian Institute of Science. Elite scientists from institutions like this and the JNCASR are now working directly alongside these young startup teams. Global efforts are currently focused on achieving a fully commercial, grid-connected fusion power plant by the year 2040. The winner of the race for clean energy won't necessarily be the nation that constructs the most expensive machine. It may simply be the innovators who learn how to outsmart the sun on a startup budget.